In 1.6, what we're going to do is we're going to look at how to find the limits of a functions by using the formula of the function itself, or using some of the limit formulas, limit laws. And previously, we look at the limit of functions geometrically and how is that interpreted. Right? And of course, we don't want to draw all every single functions and then talk about what is the limit of a particular point. So that's the whole purpose of this session. It's very important that you need to carefully look at these laws, limit laws. It said that suppose C is a constant and the limit as x approaches to a of the function f of x, and limit as x approaches to a of the function g of x exists. Okay, here's the important part. Only if each limit exists first, then the following laws will hold. First one is limit as x approaches to a of a constant. The function is a constant function. Then the limits will be also the same constant. And for that, I can quickly prove it with the geometric presentation. If a function is a constant, that's basically talking about a horizontal line, right? And if we are looking for a limit of this constant functions around a, so as you can see, the left-hand limit and the right-hand limit will be the same value as a at any point on this line. Right? Remember that to be limit to be exists, the left-hand side limit and right-hand side limit must be equal value. That's something that we learned from the previous sessions. Another example, if limit as x approaches to a of x is equal to a. Now this time the function is what? A linear function, x. So that's basically talking about here's a line. So in that situation, the same again, if we are looking for a limit approaching to a, the left-hand side limit and then the right-hand side limit, it will be what? The same value from the left side and right side approaches into graph. And these are simple, functions such that I can show you a quick, proof or geometric proof for these limit laws. Of course, anything that is, involved with operations, addition, subtraction, multiplications, divisions, and then power and then radicals, we can use the precise definitions to prove those. And that will be done in the 1.7. Okay, we're not going to prove everything, but we will learn how to prove, using a direct proof to get the using the precise definitions. So continue on. If the function is a power function, so x to the n power, and as limit as x approaches to a of this functions, then it will be the same thing as what? A to the n power. If the function is the additions of functions, right, then we can say that limit as x approaches to a of the sum of f of x plus g of x, then this is the same as, this limit value is the same as limit as x approaches to a of f of x plus limit as x approaches to a of g of x. Similarly, go for subtraction part. And these first three, actually the first 3, 4, 5, and 6 will help us to get a much more quicker property that we're going to talk about very soon, direct substitution. Right? And this is a constant multiple. Right? A function has a constant multiple. And if we are looking for the limit as x approaches to a of a constant c time with the function, then this limit value is the same thing as finding out the limit as x approaches to a of the function first, and then multiply by that constant. Right? If the functions, the limit as x approaches to a of a function, the function is a product, for example, f of x and g of x, then the limit value of that is the same thing as limit as x approaches to a of f of x times with limit as x approaches to a of g of x. So another way of saying is limit of a product function is limits of each functions multiplying together. And similarly, for the divisions part, the quotient part, if the function is a quotient, then we can talk about the limit, right, as x approaches to a of f of x divided by limit as x approaches to a of g of x. Knowing that the limit as x approaches to a of g of x is not equal to 0 because of this is rational. And you can see, as you can see, going from left hand side to right hand side, these equivalence form only will be true if each limit exists in the beginning, right? If the limits are not exist in the beginning, you can't even talk about splitting up using these equivalent form. And lastly, limits of a functions to the power, right? Limit as x approaches to a of a function to the power. That limit is the same thing as limit as x approaches to a of the function, and then raising that limit value to the power n, because n is a fix. And that, because of this, we can also apply the same thing for the radical, because radical I can think of as what a rational exponent. Right? So limit as x approaches to a of n's roots of x, that will be the same thing as n root of a. And if n is even, we need to make sure that the value of a must be greater than 0. The limit that we're approaching must be greater than 0, according to the concept of the radical. And similarly, if inside the radical has another functions, and if we are taking the limit of limit as x approaches to a of that function, then it's the same thing as what, using this property, right? We can talk about the limit of the radicand first, and then take the what nth root of it. So what we are interested in is using these property to do the examples. And the most useful one, I would say, will be this direct substitution property. And for now, we will be looking at this. If f is either a polynomial or a rational function, and the limit that we are approaching to, which is a, is within the domain of that functions, right? Within the domain of that functions, then direct substitution hold, right? Meanings limit as x approaches to a of that functions is the same thing as the function value. Remember, in last lecture, we talked about the function value and the limit values are two different things, okay? Two different things. I mean, two different ideas. Because I showed to you geometrically, the function value may not exist, right? Meaning the function may not define at a point A, but however, the limit may exist, right? Those kind of situation. So again, it is very important that you need to be careful, when you're using these, right? And I'm going to show you step by step for, a couple problems, and then we're going to try to use this direct substitution a lot more. So this is something that, we talk about it from last time. Limit as x approaches to a of a function has a limit L, limit value L, if and only if, that means it goes both way, right? The limits from the left-hand side and the limit from the right-hand side of the function, they are the same limit, okay? And yeah, this is something that I want to emphasize, because at this level, I pointed out that in my pre-calc class, a lot of theorems, we're going to be start looking at very closely to, is it a conditional statement or is it a biconditional statement? And for the direct substitution part, it is a conditional statement because if, only if you satisfy this criteria, and then we can use this property, which is the limit value and a function value as a, okay? Limit as x approaches to a of a function is the same thing as evaluating at a. So going to an example using these property. Right? Here's the following example that we're gonna do. So the very first one is limit as x approaches to 5 of the function x. So for this case, my functions, I can consider that my functions is what? Linear functions, x by itself. And this is basically the straightforward from the property that we talk, the limit law that we talk about, right? Limit of a linear functions. So it is the same thing as what? A. Oh, not A. This is 5, I believe. So therefore, in the limit value in this case is what? 5. So this is straight out from the property that we have. So let's take a look at on example number B. So example B is limit as x approaches to 5 of x squared minus 4x plus 3. So in this case, our function is x squared minus 4x plus 3. That's how we can look at it. This is a polynomial function. So by direct substitutions, if you have a polynomial functions or a rational functions, the limit that we are approaching to is in the domain of that functions, then we can use the direct substitution, meaning you can use this limit, right, value that we are approaching, use that to evaluate the functions. So we know that polynomial domain is negative infinity to positive infinity. So the limit that we are approaching to is within the domain of these functions. So therefore, we can use the direct substitutions, right? So I can say that by direct substitutions, so this will be 5 squared minus 4 times 5 plus 3, which will be equal to 25 minus 20 plus 3, which is 8. And we will be saying that this will be direct substitution. Right? Property that we use. So that's one way to approach it. And now another way to approach it is looking at this function on each term as a different, part of the functions, meaning I can look at x squared as a function, right? Let's say this will be f of x, and then g of x will be 4x, and then h of x to be what? A constant function 3. So now we are looking at in another way, x minus x, limit as x approaches to 5 of what? F functions minus g functions plus h function, this. So we can use, the limit laws to, break it down into each case by saying the limit as x approaches to 5 of f of x minus limit as x approaches to 5 of g of x plus limit as x approaches to 5 of h of x. And then you can basically do each part, which is this f of x is limit as x approaches to 5 of x squared, limit as x approaches to 5 of 4x, and plus limit as x approaches to 5 of 3. Since this is a polynomial, and then within the this is a power functions, right? X to the second power, so it's by according to the property, we can raise it, substitute it, and this is a constant multiple, so I can look at it as a constant time limit of x to the x approaches to 5 of x, and then limit of a constant is just that constant by using the property number 1. And now this is basically what the linear functions So it'll be 25 minus 4 times 5 plus 3, which will give us the same answer, 8. So this is basically broke it down one by one using the limit laws, right, to attack the problem. So two approach that you can look into it. But what I want to emphasize is this: if you are using, a simple problem like example A, and then using the property, the limit laws, then you can write it down the limit value right away. And once you write down the limit value, notice that the limit notation is dropped out. It's very important that you write your notations correctly. In part B, on the first part, that when we are doing it using the direct substitution property, after determining the direct substitution is applicable or not, then when you apply the direct substitution, notice that on that step, the limit notation is gone. I'm just evaluating the functions by using the direct substitution. As an alternative way, when I'm doing it, you can see that I write down my limit notations up until when I use the limit laws to evaluate that limit. And this is where the step or the limit notation is gone. It is very important that you write down the notations properly at this level. Otherwise, I will take out points on the exam. So please be careful when you're practicing. Okay, when to write it down and then when to take it off. So now let's take a look at on example number 3. So in example number 3, we are taking limit as x approaches to 2 of the rational function. And from this, I can right away see that the domain of this rational functions, right? Rational functions of x to the third plus 4 divided by x minus 3. This rational function, the domain is what? Anything but 3. X cannot be equal to 3. And since the limit that we are approaching to, or the limit value that we are looking for, is within the domain of the functions, we can use the direct substitutions. So by using the direct substitutions, this will become 5, 2 to the third power plus 4, and 2 minus 3. So which will give us 8 times 5 is 40, 44, and then 44 divided by negative 1. So therefore, my answer is negative 44. And right here, we apply the direct substitutions, right, for this problem. And the alternative way of doing it is looking at the numerator as a functions and denominator as a functions. So meaning I'm going to be looking at this as f of x over g of x idea for 5x to the third power plus 4 over x minus 3, like this. So when we take the limits, right, of this rational functions, so we are looking at using the property to say that limit as x approaches to 2 of 5x to the third power plus 4 over limit as x approaches to 2 of x minus 3. And I can use this equivalent form, the limit law, because the limit as x approaches to 2 of the numerator functions exists, and as well as the denominator function exists. That's the only time you can split it out. If one of the function does not exist, then it's not going to work. So on the numerator, you can use this step-by-step, breaking it down, or you can use the direct substitution idea to go for it. So if I'm doing step-by-step, then I'm looking at limit as x approaches to 2 of 5x to the third power plus limit as x approaches to 2 of the constant 4. Similarly, in the denominator, limit as x approaches to 2 of x minus limit as x approaches to 2 of constant 3. And this is, in this first, the numerator, the very first term is a mod constant times the power functions. So therefore, I can look at it as a constant times the limit of the power function. And then plus limit of a constant is a constant. And notice that I dropped out the limit notations already because I evaluate that term by using the law. And also in the denominator, the very first term, if I use the limit law, it will be just 2. And then constant of a limit is just a constant. So every time I evaluate it, I dropped out those limits. So you can, write it down step by step like this. So lastly, it will be 5 times. Limit of, power function is just 2 to the second power plus 4 over -1. So it will give me the same answer, which is 44 negative. Right? So, you should practice it how to write down step by step a few of them to make sure that you know how when to drop it off the limits notations and when not to. And if the easy the on the test whenever you can apply the direct substitutions, I will recommend you use that so that it will shorten it. Right? So let's take a look on the next example. So the next example is limit as x approaches to 2 of x to the second power minus 4 over x minus 2. Right? So as you can see, in this case, the functions is x squared minus 4 over x minus 2. And the domain of this rational function is anything but what? 2. But the limit that we are approaching to is exactly where is not in the domain, not a part of the domain. So therefore, according to the direct substitution, I cannot use direct substitutions at this point. Okay. Now, if we cannot use the direct substitution, then I may think about this way also. Hey, can I use, the quotient rule, thinking about the numerator as a function and denominator as a function, right? And that could apply also. Right? So when you talk about this kind of functions, hey, okay, I can see the limit as x approaches to 2 of x squared minus 4. Hey, that's okay, right? Because it's the limit exists, and limit as x g of x limit as x approaches to 2 of g of x, which is going to be x minus 2. That limit also exists. That's okay. But however, what happened is this criteria doesn't meet. Limit as x approaches 2 of g of x cannot be equal to 0. That does not, right, meet. So therefore, I cannot even split it up from this limit, right, from this limit to here, because although the limits on the numerator g functions exist, the limits in the f functions exist, but the g function is what? Equal to 0. The limit as x approaches to 2 g function equal to 0. So this criteria doesn't meet. So that is the problem. So now direct substitution doesn't work, and then limit laws, one of the criteria doesn't meet, so we cannot approach it either. So in this kind of situations, what do we do, right? So now the question raised up will be like, oh, what technique do I need to use, right? Does the limit even exist or not? So let's take a look at and review very quickly on this. That's why I purposely put this very easy functions so that we can recall what we learned in pre-calc. So if I have a functions that is x squared minus 4 over x minus 2, and we see that minus 2 and x plus 2 and then x minus 2 reduce it. So in the pre-calc, we learned that in the rational functions, when we can simplify the same common factor, right, in the rational functions, and this is not what a vertical asymptote anymore. This is what a hole in a graph. A hole at where? A hole at 2 in this case. So our graph is, here's a linear functions, x plus 2, 1, 2, and then here's my y-intercept, and then the slope is 1. So go up 1, out 1, go up 1, out 1, so on and so forth. This is a line, which is x plus 2, right? The line. But however, we know that x cannot be equal to 2. So at this point right here, there will be a hole, right? That's what we learned in a pre-calc, how to draw pre-calc or college algebra, right? Or algebra 2. And this is a hole. But from this graphical presentations of these functions, I can see that the left-hand side limit and right-hand side limits will be what? The same on that whole. Okay. So that sort of tells me, you know, when we approach it to 2 from the right-hand side and left-hand side, our limit value is the same. But the function, in this case, notice that the function does not exist, right? But the limit value will exist. So we saw that this kind of problem on the the graphical problems on the previous sessions. So that sort of tells me, hey, there must be a way to do this, right? There must be a trick on the limit that we can use. So here's the trick. Okay, here's the notes that you need to put. The limit of the original function is the same thing as the limit of the simplified function. Because remember, the idea of the limit is what? We are looking for what is the limit values going to be when we approach to what? 2, not exactly at 2, right? Because exactly at 2, the function may not define. In this case, the function does not define. Right? So it's very important that you clearly understand the limit value, the difference between the limit value and then the function value. So the limit value is basically talking about what? When we approach into this x value, what is the limit outcomes going to be? So therefore, this is a very important example. Help us to use this little trick. So I will put a 3 star and then put a note. All right. So what is a note in this case? And that's what we want to look at. So here's notes. If the limit of original functions is, I should say, the limit value, right? Oh no, that would make the limits is a value, or limits of a function is a value already. So limit of a function is same as limit of simplified function. So that is the trick that you need to remember, so that in this kind of situations, in other type of problem, you can expand and think about it. So now that we see graphically what's happening, and then here's the notes that we put it down, now I can compute. So this will become limit as x approaches to 2 of x minus 2, x plus 2 divided by x minus 2. So this will give us limit as x approaches to 2 of x plus 2. So we simplify the functions of the limit. Now, in this case, because of this is a polynomial functions and S2 is a domain within this polynomial functions, then I can use the direct substitutions at this point. Okay. And that will be what? 2 plus 2, which will be equal to 4 is my limit in this case. And make sure you clearly understand this example. Let's take a look at the next example. Example number 5 is another example that is very, example number E is another example that is very important for us to understand, how to, attack the limit problems on the piecewise defined functions. In this problems, we want to look at the limit as x approaches to 1 of g of x. And then defining g of x as a piecewise function, x plus 1 if x is not equal to 1. And when x is equal to 1, g of x is equal to pi. So it's, in this kind of situations, like, how do I find the limits? A lot of times the mistake is thinking, when x is equal to 1, my g of x is the value is what? Pi. and right away quickly write it down to pi. And remember, the limit value and then the idea of the limits and then the function values are what? Different. Okay. So if it is a function value, g of 1, then yes, I will be saying what? Pi, because I cannot use this first formula because the input that we are looking to evaluate the function is not within the formula of the first restricted domain, right? Not in the restricted domain of the first formula. So therefore, I use the second formula to evaluate the function. But the limit is the difference, okay? When we say that limit as x approaches to 1 of g of x, we are looking at on the x-axis, here's 1. As x approaches to 1 from the left-hand side and x approaches to 1 from the right-hand side, are those two values the same or not? Or they are approaching to the same value or not? So therefore, it is very important that when you say the limit as x approaches to 1 of g of x in this kind of situations, right away, I have to think about, right? We need to think about this basically mean, right? I need to look for a limit as x approaches to 1 from the positive side of g of x and limit as x approaches to 1 from the left-hand side of g of x. Right? Because we are not looking at 1. So to illustrate that, I drew the picture because not necessarily all the time you will be able to draw the picture very quickly and then find the answer. So as you can see, the first formula is a linear equations, y-intercept at 1 and the slope at 1. X is not equal to 1, so therefore there is a hole right here. And then for the second formula, when x is equal to 1 for this g function is a constant, which is what? Pi 3.14 around there. Here's that is. But when we talk about the limits, we are talking about x approaches to 1 from the right-hand side and then the left-hand side. So what we need to do is we need to look at where it's going. So from the right-hand side, according to the picture, right, the graph is approaching to what? This hole. And when we approach it from the left-hand side, also the graph, right, the value, function value, is approaching to this hole again. So therefore, it is very important that you need to understand, what functions we need to use. So when we approach into 1 from the right-hand side, we are still talking about what? This formula of this line. So therefore, I can say that this is limit as x approaches to 1 from the positive side of what? The formula will be x plus 1. And since this is a polynomial functions, right? X plus 1 is a polynomial, so I can use the direct substitutions to evaluate it, which is 1 plus 1, that is equal to 2. Now, that doesn't mean that the value of the limits is 2, because remember the theorem said that only if the left-hand side limit and right-hand side limit, if they are the same, then we can talk about this as a limit. So now the question is, what is x approaches to 1 from the left-hand side? When we approaches to x from the left-hand side, graphically looking at it, is still on this line that we are taking. So therefore, the formula will be, again, x plus 1. Not necessarily all the time is like this. Okay, you have to be careful that we're going to talk about another example very soon to make sure that you clearly understand. So this will become, again, polynomial, so I can use the direct substitutions on this step. So that will become 1 plus 1, which is equal to 2. Now you can see that the left-hand side limits and the right-hand side limits, they are the same. Therefore, by theorem, I can conclude that limit as x approaches to 1 of g of x, that is equal to 2. That will be my final answer. And notice that this one happened to be, we are talking about, looking at the same formula, even though you go from the left-hand side and right-hand side. Not necessarily all the time is like this, and we're going to talk about more example on that. Now let's move on to the next example, F. So for example F, limit as x approaches to 0 of x minus 2 quantity square minus 4 all over x. So right away, I can see that for this rational functions, x minus 2 square minus 4 over x, we know that the domain is everything except 0. And the limit that we are approaching to is not within the domain. So therefore, direct substitutions cannot be applied right away. So from example D, right, we already saw one case before. So now the question raises up to me, hey, can I simplify this? Right? Because from example D, we know that the limit of original function is the same as what limit of the simplified function. So now let's try to simplify these functions and then see what do we get. So limit as x approaches to 0. When you FOIL this, this will be x squared minus 2x plus 4 minus 4 over x. So which is give you limit as x approaches to 0 of x squared minus 2x over x. Now factoring out x and then reducing it, which give us, the limit as x approaches to 0, that is x minus 2. Now it is a polynomial function with, the limit is within the simplified polynomial function now. So therefore, I can use the direct substitution at this point. And the limit notation will be drop out, which is 0 minus 2. That is equal to negative 2. And this will be my final answer for this example. Then let's take a look at on example G. Example G, again, limit as x approaches to 3 of x minus 9 over x minus square root of x minus 3. And as you can see, this functions x minus 9 over square root of x minus 3. Domain is everything except x is equal to 9. Oh, I think I copied it wrong. Yes, the limit is approaching to 9. So that's the purpose of this example. And x is what? Everything, the domain of this function is for everything except 9. Right? So once again, this is the rational functions that I cannot, the limit that we are approaching to is not within the domain of the rational function. So therefore, I cannot use direct substitution. So unlike the previous example that we see, I cannot really simplify this. Right? I cannot factor and then reduce. So what you can do in this case is, you need to consider either rationalizing the numerator or rationalizing the denominator to continue and then see, can I simplify the function or not? So in this case, since the radical is in the denominator, I'm going to try to rationalize the denominator and hoping that, it's something, come down into the format that we want or the property that we can apply. So I'm going to multiply by square root of x plus 3 multiplied by the conjugate factor plus 3. So which will give us limit as x approaches to 9 of, I will leave it as in a factor format because if you multiply it out, anything that we need to, because the main thing is I cannot use direct substitution because of the denominator part. So we are hoping that after we rationalize it, the denominator, the entire factor will be reduced, right? That's our hope. So therefore, in this kind of situation, I'm not going to try to multiply it out on the numerator. I will not multiply it out. So leaving as this to see anything happen. So this is the difference of 2 squares. So square root of x squared will be x, and then minus square root of 3 will be, 3 squared will be 9. So as you can see, after we rationalize the denominator, there is a factor that can, nice and neatly reduce, and then this will give us limit as x approaches to 9 of square root of x plus 3. Now, the functions that we have right here is not a polynomial or a rational functions, right? Because at this point, direct substitution property only allow us to consider for what? The polynomial functions and a rational function, not the radicals and stuff. So therefore, I'm not going to use the, the direct substitutions. I have to use the limit law until we talk about the next, the whole entire chapter 1, which is the rest of the properties. Then we can apply that very quickly. So on the exam 1, then because of we already talked about all the properties already, the whole entire chapter 1, at that point you may skip these following steps that we're gonna do. So at this point we have no choice, very limited amount of laws that we know. So I have to split it out for additions. And this, right, square roots property, we have a limit law saying that square root right here, right? So nth root, limit as x approaches to a of n root of x, that is the same thing as what nth root of a. So it seems like it's a direct substitutions, but we haven't really talked about this property yet, so that's why we need to split it out. Now this will become what? Square root of 9, and then limit of a constant is a constant, so therefore it will be 3 plus 3, which is equal to 6. Right? So this step later on, you may, after we finish the entire chapter 1 and then learn the rest of the property of the limit, then we may skip this step and then think about the direct substitutions idea again. And this is the end of example G. And then let's take a look at another example. Example H. Limit as x approaches to 0 of square root of x squared plus 9 minus 3 over x squared. So this problem is similar to the previous one. As you can see that the rational functions, the domain is everything except 0. But however, the limit that we want to find is x approaches to 0, which is not a part of the domain. So therefore, direct substitution cannot apply directly. In the previous example, we learned how to deal with the functions that involving radical expressions, which we rationalize the denominator. So in this case, you can see that, one way to simplify this function is rationalizing the numerator. So I want you to try, pause and then try to rationalize the numerator and then see what you get. Okay. Okay. So rationalizing the numerator is basically multiplying with the conjugate factor. And in this case, the conjugate factor is square root of x squared plus 9 plus 3. And then we're going to multiply both numerator and denominator. And that will help you to see that the numerator will be a difference of square. So therefore, when you multiply it out, that will give me x squared plus 9 minus 9. In the denominator, as before, I'm going to try to write it in terms of product. Make sure you write it with appropriate grouping symbol, which is with the square root inside the parentheses. Right? So as you can see, once we simplify further, that will become x squared all over x squared times square root of x squared plus 9 plus 3. And the x squared part, reduce it. So therefore, I will have 1 over square root of x squared plus 9 plus 3. Now, this is a rational functions, and a 0 is within the domain of this rational functions when we are trying to approach. And this is where the direct substitution is applicable. So applying the direct substitutions, the limit notation is gone, and that will become the square root of 0 squared plus 9 plus 3. So finally, simplifying out this give us 1 over 3 plus 3, which is 1 over 6. And that will be the final answer. Let's take a look at on the next example I. Example I. Limit as x approaches to 0 of the function absolute value of x. This example is very similar to example E, because absolute value, we don't know how to take the limit of absolute value. Right? There's no limit laws allows you to do any of these functions at this point. So the way that we need to do is we need to look at this absolute value function as a piecewise defined function, and looking at where the limit is approaching to, where we want the limit. And that's the reason why in session 1.1, we want to know how to write down the, review the absolute value a little bit, right? So absolute value of x, right? According to the definitions, the piecewise defined function is, it will be x if the value of x is greater than 0, 0 if x is equal to 0, and negative x if x is less than 0. Because only if when the x values are less than 0, negative of a negative number, the outcome will be positive. That's the key thing that we're looking at. When we look at the graph of this, that is basically this right here. Absolute value graph is a V shape. So when I say the limit as x approaches to 0, you need to understand. We need to clearly understand that the limit value is different than the function value, right? We cannot say that we are not talking about f of 0, which is absolute value of 0 equals 0. No, not this one. So what we are looking at is from the graph, we can see that when x approaches to 0, right, from the right-hand side, we are using this part of the graph, which is basically using anything that x is greater than 0. So we are using this function, right? The formula of the function will be x. But when x is approaching to 0 from the left-hand side, then we are using this part of the graph. And this graph is basically using this formula right here. So it is very important that you need to understand where the limit is approaching to. If the limit that we are approaching to, okay, involved in two different restricted domain part, then we're gonna have to start thinking about left-hand side and right-hand side limit. Right? So being said that, when we want to look for this limit as x approaches to 0 of the function's absolute value of x, then we need to think about limit as x approaches to 0 from the positive side, and the limit as x approaches to 0 from the negative side. And this time, right, unlike example number E, approaching to the right-hand side, which is this portion right here, is using, the first formula, x. When we approach to 0 from the left-hand side, we are using this part of the graph, which is what? Negative of it. So my function formula will be negative x. So that is the difference between example E and in this example, because we are talking about two different parts of the graph with the different restricted domain. So the formula for each part is different. You have to be really careful about that. Okay? So to make it more clear later on, I'm going to point out, once again, here's the important part that I'm going to repeat it. If the limit that we are approaching to involve in two different restricted domain part, which is right here and right here, right? Then we're gonna have to think about either left-hand side and right-hand side cases, right? So now, in order to find out this limit, we evaluate this limit approaches from the right. So limit as x approaches 0 from the right-hand side of x, that is basically using the very first, second limit law, that will be 0. And also limit as x approaches 0 from the left-hand side of negative x, when I use the limit law, that will become negative of 0, which is still going to be what? 0. Since the left-hand side limit and right-hand side limit, they are the same, then I can now say that limit as x approaches to 0 of absolute value of x, the limit will be equal to 0. So as you can see, both from approaching from the left-hand side and the right-hand side, the limit value will be what? 0 at this point. Okay. So it is an important example that you need to understand so that, you can clearly look at, how to look at the piecewise defined functions. Let's take a look at on another example, J. So example J is very similar to I. We are looking at limit as x approaches to 0 of x over absolute value of x. Right? But the difference, the main difference right here is this is a rational function. And then plus, okay, the domain of this rational functions does not include 0. So therefore, direct substitutions cannot use. And also somehow we cannot just use with absolute value to evaluate. So what we want to do in this case is we want to, simplify this function. So in order to simplify these functions, the limit that we are approaching to is 0. And we already see from the previous example, absolute value of x, for absolute value of x, when we approach a limit as x approaches to 0, what's going to happen is we're going to have to break it down into cases. So if you look at the function x over absolute value of x, then what we see is for x value that is greater than 0, right? Then the absolute value of x will be just what? X, because the output of the absolute value will be always positive. Because of the restricted domains all positive, so I don't need any extra additional part. I use a different color to help you to see better. But when the x value is less than 0, then I cannot just write down x anymore, because remember, output of absolute value of x must be always positive. So when x value is a negative, then we will have what? Negative x. For this particular case, the function does not define at x equal to 0, right? Because we don't know what is the meaning of 0 over 0. This is called indeterminate form, in which we haven't talked about that yet. Once you go into chapter calculus 2, you will talk about indeterminate form of the limits of the functions. And then you will learn how to continue using those, okay? A different theorem. So therefore, in this case, when x is equal to 0, this is like indeterminate. So we don't want to talk about the 0 case at this point. So with this too, you can sort of see that, the limit that we are trying to approach to, which is 0, involved in what? 2 different parts of the restricted domain of the functions. So that basically tells us we're going to have to use what? The right-hand side and the left-hand side approach. This says. So therefore, when we look for this limit, first we're going to talk about limit as x approaches to 0 from the positive side. And one positive side, that means what? Approaching to 0, x is greater than 0. That will be coming from the right side. Then we are using this function, which is x over x. And when we talk about the limit as x approaches to 0 from the left-hand side, and then we have this part, we're going to be talking about the second portion of this piecewise defined function, because restricted domains is x less than 0, so coming from the left-hand side. Remember, that is very important, that we need to be able to, rewrite it. So now, again, direct substitution still is not applicable because 0 is not within the domain of this rational function. But because of we rewrite expressions without absolute value, that allow us to simplify, right? That allow us to simplify the functions, which is going to be limit as x approaches to 0 from the positive side equal to 1 of 1. Limit of a constant is a constant, so therefore it is 1. when we talk about the limit as x approaches to 0 from the left-hand side, and we cannot use direct substitution, so we simplified it, right? After we write down the functions without absolute value, we can simplify, and then that gives us -1. And limit of a constant is a constant, so we got -1. Since the left-hand side limit and right-hand side limit, they are not equal to each other, now I can conclude that, right? Limit as x approaches to 0 of the function x over absolute value of x does not exist. So the limit does not exist, meaning there is no limit value in this case. And in short, from now on, we're going to write down this is D and E. Limit does not exist, right? So this is a big difference between the previous example and this example. So the key part is understanding how to write the functions without the absolute value with the proper restrictions, so that you can think about, okay, the limit needs to be done with left-hand side or right-hand side limit in order to find that out. So you might have a questions. Let me see, EFGH K. Let's take a look at on example K. So example K will be the same similar one that we're gonna look at it, and then L, I will point out what is the difference. Like, one, we don't need to break it down into like 2 cases, right? So let's take a look at on example K. So example K, we are looking at limit as x approaches to 2 of x minus 2 over absolute value of x minus 2. So as you can see, this rational function is very similar to the previous example. The limit that we approach into is not within the domain of this rational function, because x cannot be equal to 2, right, in the denominator. And so what we need to consider now is like, can we simplify, right? So when we want to simplify it, we need to know how to write the functions, right? X minus 2 over absolute value of x minus 2 without the absolute value. So using the definitions to write down the piecewise defined functions. And this is where how you can think about this very easily and quickly. And we know that absolute value of x minus 2, right? And the first question is which x value will make this entire expression will become 0, right? X. So that will be what when x is 2, because that's going to be 0. So anything that on the right side of 2, that will give me a positive result, and anything the left side of 2 will be negative result. We can plug it in and check quickly. If I plug it in 3, 3 minus 2 is a positive number. If I pick 0, 0 minus 2 is a negative number. See that? So therefore, right away, I can see this very clearly. So here's the trick, find out the 0 part first. And that's where you're gonna be putting your restrictions. Your restriction will be when x is greater than 2. A lot of time, the mistake that I see usually is, get dragged along by always thinking absolute value x must be greater than 0 or less than 0. No, that's not true. Depending on what you have inside the absolute value, right? So in this case, when x is greater than 2, we will get a positive result all the time. So therefore, I don't need to have any extra things to add it down. And when x is less than 0, or less than 2, right? We know that this expression, x minus 2, will give me a negative result right here. So therefore, to make sure the outcome of the absolute value is always positive, it will be negative of x minus 2. Negative of a negative number will be positive result. So that's how you can think about, by looking at this, visualizing the real number line and where the 0 is going to be. That's how you can think about the restrictions very easily. And we talk about that in our pre-calc class, right? If you take a pre-calc class in a different college or university, I'm hoping that these fundamental part has reviewed it. Otherwise, please make sure you ask me, right? Later on in the class. So now the limit that we are looking for, right, is as x approaches to 2, and that is in the two part of the restricted domain, right? Both, the right-hand side and left-hand side involved. So therefore, and this is the limit that we need to break it down into two cases, which is the limit as x approaches to 2 from the right-hand side and the limit as x approaches to 2 from the left-hand side. So from the right-hand side, we will get the functions will be x minus 2 over x minus 2. For the left-hand side part, we will get the functions x minus 2 over negative of x minus 2. So simplifying this, evaluating this limit, I cannot do the direct substitution because the domain is not within the limit is not within the domain of the functions. So when I simplify it, this will be limit as x approaches to 2 from the positive side of 1. Limit of a constant is a constant. When I simplify the limit from approaching to 2 from the left-hand side, right? Again, the same idea. We try to simplify the functions because direct substitution is not applicable. And this gives us limit as x approaches to negative 2 from the left-hand side of negative 1. Limit of constant is a constant. And now we can see again, the left-hand side limit and the right-hand side limit are not the same. So therefore, this tells us the limit as x approaches to 2 of the function x minus 2 over absolute value of x minus 2 does not exist. The limit value does not exist, right? Because of the left-hand side limit value and the right-hand side limit are not. So far we have seen two cases, right? Two example, the same situations when we need to use the left-hand side limit and right-hand side limit. And that basically, if you really understand it, that's good. Or if you missed out a point, you will confuse that whenever you're looking at the piecewise defined function, you might be thinking you need to do the left-hand side limit and right-hand side limit, which is sometimes is not necessary, right? So that's why it's very important. Let me repeat this again. When we are evaluating the limit that we are approaching to, the x value, right? When x is approaching to a value, and that value is involved in both or more than, right, restricted domain, most of the time both left-hand side and right-hand side, then we're going to have to use the left-hand side limit and right-hand side limit approach, right, to find out the limit. Now I have an example that don't need to, so that it will help you to see clearly on these example parts. So let's take a look at our next example. So example L, limit as x approaches to 4 of g of x. So in this case, g of x is defined, given as a piecewise defined functions. We will use the first formula x squared minus 5 if the domain, right, x is less than or equal to 3. And we will use the formula square root of x plus 3 if x is greater than 3. So two different restricted domains. So now the question is limit as x approaches to 4 of g of x. What is the limit? Right? And we have a piecewise defined function. So now the question is from the previous example, you might be thinking that, oh, I need to use the left-hand side limit and right-hand side limit. Then my question will be, do we really need it? Right? That's the key part that we need to consider. So we use the left-hand side limit and the right-hand side limit, right, for absolute value case like this before, because the limit that we are approaching to is at 0, which is approaching from the left-hand side and right-hand side. We have different portion of the graph, which representing different formula. But however, if you look at on this problem, the limit that we are approaching to, x is greater than 4. Right? When x is greater than, when x is 4, and limit as x approaches to 4, and that is basically in the domain of the second formula. And we know that in the second formula, x must be greater than 3, and then we are talking about a radical, which is a graph something like this. So when we are approaching to 4 from the right-hand side and the left-hand side, we are still using the same graph, right? We are using the same graph. We don't have to use two different formula to talk about the same graph. So I want you to sort of visualize and interpret it. I want you to get that idea, but not all the times we will be able to visualize the graph. So that's why you need to learn how to look at the domain part of it, right? So 4, right? Limit as x approaches to 4. This 4 is not in the restricted domain of what? Both of the cases. So therefore, I don't need to use what? Left-hand side limit and right-hand side limit. So in this case, when we talk about limit as x approaches to 4 of g of x, since 4 is in the restricted domain of the second formula, this g of x will be square root of x plus 13. And we don't need left-hand side, right-hand side. The reason why is because this is a radical function. And now we can use the limit law to talk about the square root limit of a radical function is the same thing as square root of limit of the radicand. Since the radicand is the polynomial, so I can use the direct substitution. So that will be square root of 4 plus 13, which is going to be square root of 17. And that will be my final answer. So now making sure that you understand the big difference right here when to use the left-hand side limit and right-hand side limit on this piecewise defined functions. Once again, let me repeat this. In the previous examples, right, the limit that we are approaching to is in the domain of both restricted domains, right here. So therefore, we need to use left-hand side limit and right-hand side limit because the formula for each case is different. As well as on example K, the limit that we are approaching to, right, that is in both restricted domain. So therefore, the formula for each case is different. Therefore, I have to use the left-hand side limit and right-hand side limit to check the limit is the same or not. But however, in this case, the limit that we are approaching to is not in both of the restricted domain, only one. So therefore, I just have to use this formula because from both left-hand side and right-hand side, and this limit, is using the same formula. So hopefully you see the big difference that I'm pointing out and then understand. So let's move on to the next example. Example M, limit as x approaches to 1 of g of x, and where g of x is defined to be piecewise defined functions right here with the restricted domain. X is less than 1, we will be using the formula x negative x squared. When x is equal to 1, we will be using the formula 2, and when x is greater than 1, we will be using the formula x minus 2. So we are looking for the limit as x equal to 1 of g of x. So what is the functions, right? Which formula do we need to use for these functions? And this is where we decided to look at what? The limit that we are approaching. This time we are approaching to what? Limit x approaches to 1. And then we found out that the limit that we are approaching to involve in every part of the restricted domain, which we don't really have to worry about this middle one equal to part because we want to talk about the left-hand side and the right-hand side. So therefore, for the left-hand side, we will be using the first formula. For the right-hand side, we will be using the last formula. And then try to see the left-hand side limit and right-hand side limit, are they the same or not? To talk about the limit of this function. So limit as x approaches to 1 from the positive side. and limit as x approaches to 1 from the negative side. From the positive side, which is this part right here, right? And we will be using the formula x minus 2. From the left-hand side, right, when the restricted domain is less than -1, that's from the left-hand side, we will be using the first formula, which is negative x squared. Now, since x minus 2 is a polynomial, so we can use direct substitution. Right? So that will become 1 minus 2, which will give us -1. And for the other case, x squared is also negative x squared is also a polynomial, so therefore we can use direct substitution, and which will give us -1 to the second power, and that will also give us -1. Since the left-hand side limit and right-hand side limit, they are the same, therefore I will be able to talk about the limit as x approaches to 1 of this piecewise defined function g of x is equal to -1. We do have a limit value. So hopefully these examples, right, help you to see clearly when to use left-hand side limit, right-hand side limit, when not to. And let's take a look at on the next example. Example N. This is another different type of approach that we need to, the type of problem that we need to use a different approach, right? So the problem is limit as x approaches to 4 of 2 minus x over x minus 4 times with x plus 2. It is the rational functions, and the limit that we are approaching to is not in the domain of rational functions, because we can see that in the domain of this rational functions, x cannot be equal to 4 and x cannot be equal to what? -2, and which the limit that we are trying to approach, right? The limit that we are trying to find is x approaches to 4. So in this kind of situations, how do we deal with it? Right? This will be very similar to, like, the last two examples that we did in the previous two problem. And also you need to remember and then know that in order to find out this limit, we need to use what? The left-hand side and right-hand side limit approach. Because quickly looking at the graph of this functions, I can right away see that, at 4 will be a vertical asymptotes, at -2 will be a vertical asymptotes. So we clearly want to know from the left-hand side when we approaches to 4 what is happening, and also from right-hand side when we approach it to 4 what is happening. Okay? So I can sort of use a plug-in number idea to plug it in and then try to think about the number and then write it in descriptive format. And that is something that I emphasized last time. Right? So let's say if I try to approach from the right-hand side, right? So we are looking at what? 0.00004, 4.00001, very, very close to 4, but from the right-hand side. And if I use this number and plug it into this rational functions, the numerator will be a negative number. The denominator will be a positive time a positive number, so the result is negative. But the numerator value will be very, large, and the denominator value will be very small. So we will be getting a very small negative number, which is what? A negative infinity. Now, if I approach this to this 4, right, from the left-hand side, we are looking at number 3.9999, this number. So if I plug it in this number into the functions, right, we will be getting the numerator will be a negative number, and divided by the denominator, the first factor is a negative, and the second factor is a positive. And then this will tell us negative divided by a negative, which is going to be a positive value. But because of the denominator will be a very tiny number, right? And then a bigger number divided by a very tiny number, it will go to what? Positive infinity. So this is very similar to what we talk about also in our pre-calc class. I give that idea in a pre-calc so that you can think about this in this. But anyway, the key point right here is we need to find out the left-hand side limit and the right-hand side limit. In this case, I already found that already right here, right? But this graphical presentation is not, right, the answer that I want. This is only for you to visualize and think about it. How the graph is going to be behaving around the vertical asymptotes, right? And which is the idea of the limits that we are talking about from the previous sessions. So in this case, for the limit as x approaches to 4 from the right-hand side of the functions, and this is how we want to write it down and explain, right? And this will be what going to, from the right-hand side, is going to what? Negative infinity directions. Remember, from the last example, from the last sessions, this is not a limit. It just only tells you where the directions of the limit is going. Okay, the limit does not exist. And the way that we can write it down and explain it is, like we did before. Let me write in different color. As x approaches to 4 from the right-hand side, the value of 2 minus x is a small negative value, or a small negative number, and the value of x minus 4 times with x plus 2 is a very, that's how we will, emphasize it, small positive value, right? Positive number. Therefore, 2 minus x divided by x plus 4, x plus 2 is very large, right? Negative number. And that's simply saying what? Going to negative infinity. So similarly, I'm going to do the same thing, copy and paste limit as x approaches to 4 from the left-hand side of the functions x minus 4, x plus 2, and that will be going to positive infinity. And the explanation will be the same, just copying this down, and then every little things will change from here, right? So let's try to write that. So when we talk about the descriptive formats, I use a black ink to change the things. So as x approaches to 4 from the left-hand side, the value of x 2 minus x is a small negative number, but when we look at on the value of x minus 4 times x plus 2, that is a very small negative number. That's where it changes. So a negative number divided by a negative number is a very large negative number, a very large positive number. That's why there's positive infinity. So therefore, in this case, I can see that even though the limit does not exist on each left-hand side case and right-hand side case, right? Only talk about the directions. And so therefore, since directions are different also, so I can say that the limit as x approaches to 4 of 2 minus x over x minus 4, x plus 2 is what? Does not exist. We know that both left-hand side limit and right-hand side limits are does not exist. But however, if they go to the same direction, like in previous sessions I mentioned it, if they go to the same directions, we can sort of like talk about the limits going to what? Positive infinity directions or negative infinity directions. But the limit does not exist, right? All right, so let's take a look at on the next problem. So example O, the last example of using this limit laws, right? And in this limit, you can see that limit as x approaches to 1/2 of square root of 2x minus 1. This is the square root, functions. And we know that the square root function in this case, that is basically talking about, um, at 0 will be a negative number. So it's starting from 1/2. So my square root function is from here to there. And remember, the limit that we are approaching to is at the value of 1/2, right? We are looking for the limits at x equal to 1/2. So, but if you look at the sketch that I draw, right, there is no way that I will be able to talk about the limit from the left-hand side in this case, because there is no graph at all, right? There is no graph at all. So in this kind of situations, you have to recall from the previous sessions, we talk about one-sided limit, and you need to write it appropriately. So looking for the limit as x approaches to 1/2 of square root of 2x minus 1 is the same thing as talking about one-sided limit, which is limit as x approaches to 1/2 from the positive side. You need to indicate it correctly, which limits only apply in this kind of situation. So square root of what? 2x minus 1. And by using the limit law, I can basically talk about limit of the square root is the square root of the limit, right? As x approaches to 1/2 from the positive side of 2x plus 1. Since the radicand is a polynomial, so I can use the direct substitutions. And that means this will be square root of 2 times 1/2 minus 1. And remember, you write this as a apposcript so that you indicate positive is the right-hand side. So computing this, that will give me square root of 1 minus 1, which is going to be what? Equal to 0. So therefore, my limit is 0 in this case. And that is all the examples using the limit laws and a direct substitution probably. And then what we're going to do now is continue looking into the important theorems, right? The very first theorems that this chapter, important theorems of this chapter, this sections. So the first theorem tell us what is happening on the limits of the functions, the limit values when the functions have like what inequality involved, meaning one function is smaller than the other functions or one function is greater than the other functions. So in the theorem, right, the way that I look at the theorems is a conditional by conditional statements. And the theorem said that if, that's a conditional statement, if f of x is smaller than g of x, when x is near a, right? So that means this f functions does not have to be always, right? The function value does not have to be always smaller than g functions. But whenever, the x value is what? Near the limit that we want to talk about, this situation is happening, f function is smaller than g. And that's important. And the limits of f and both g both exist. Okay, both functions, the limit must be exist. So in this conditional statements, we need to first satisfy two criteria. One is f function must be smaller than g functions around where we want to find the limit. And in both of the g functions and the f functions, the limit must exist. Only if those two conditions met, then we can talk about the limit as x approaches to a of the f functions, that limit value, will be smaller than or equal to the limit as x approaches to a of g function. Okay? So this is like, if then kind of statement. And what does that mean? Once again, criteria 1 and then criteria 2 must be met in order to use this conclusion part. So graphically, this is what's happening. Right? We are looking at, here's the limit that we want to approach A on the x-axis, and then y-axis, this is y-axis. So let's say that my f functions is something like this. My f function is something like this. Right? The graph of f functions look like something like this. And my graph of g functions, right? The graph of g functions look like this. So notice that, you know, on the f function is not all the value of f function is not smaller than g functions in the entire domain. But however, the value of f function is smaller than the value of g functions around what? Near where we want to find the limits. Okay? So as you can see, around where we want to find the limit, the value of f functions is smaller than what? The value of g functions. This is f of a, and this is g of a. So if that's conditions met, right? And then notice that because of this is a polynomial functions that I'm drawing, so both limit exists. So therefore, I can say that this conclusion is true. And why do we need this, right? This is gonna help us, right, on the next very important theorem, which is called the squeeze theorem. And squeeze theorem is basically what using inequality, compounded inequality with three functions together. So let's take a look at on the squeeze theorem, which is something that we want to use later on. So the squeeze theorem state that if f function is smaller than g function is smaller than h functions, right? Somewhere near the limit that we want to find. So not necessarily the entire functions that we're talking about. Then the limit of f functions, which is the lower bound right here, okay, which is the lower bound functions, and the limit of g functions, oh no, the limit of h functions, which is the upper bound functions right here, right? If their limits are equal, then here's the conclusions. Then we can say that, okay, we can say that the limit as x approaches to a of g function have no other choice but to be what? The same limit as the other two. Okay? That's what it's saying. So once again, in here, you have to map two criteria. One, the function must be what? Bounded between the lower bound functions and upper bound functions, which is this one. And then second, which is this part right here, right? Which is this entire part, which is what? The limit has to be what? The limit of the lower bound functions and the limit of the upper bound function, it must be the same limit. Then we can talk about the limit of the functions in the middle has to be the same limit as the other two. There's no other choice. So what does it graphically look like in this case is something like this. So graphical representation is, you're looking at something like this right here. So here's my y-axis and an x-axis. And let's say this is my, this is where I want to find the limit as x approaches to a. of the functions, and which functions we are talking about. Here's my h functions. Okay, and here's my, f functions. Let me write it down. Here's my f functions. Oh wait, no, this is h because this is going to be upper bound. Right? Here's the h functions, and here's my the lower bound function, f functions, something like this. And here's my g functions. So notice that, not entire domain, everything's like this, but however, at this point, you can see that, the point that I'm making is where I should be careful with this, because let me regraph this. I can graph it like this, because the reason why I'm regraphing it is because what the g function has to be between f function and h functions near a, which is like in one is close to a, then it has to be what the function has to be in order, right? Increasing to decreasing order. So that's why I'm redrawing this part right there in the middle part. So as you can see, all of them is going to be like bounded. The g function will be bounded with f function, h functions, and f functions. And if the limit of h functions and f functions are the same at a, then g function has no choice to be the same. So this is called a squeeze theorem, right? Because the middle part, the middle function got squeezed, or also known as the sandwich theorem. So what we want to do is we want to use this, squeeze theorems to find out some limits that are not going to be able to use any of the technique that we talk about so far. So looking at the example, which is something like, involving sine and cosine. So show that limit as x approaches to 0 of x squared, sine of 1 over x is equal to 0. And clearly, I cannot use the direct substitutions, first of all, because sine, it's not polynomial functions. We haven't talked about any trigonometric function yet. And plus addition to that, when I plug in 0, 1 over 0 is undefined. I cannot do anything, right? So in this kind of situations, then we're going to start thinking about, is there any limit law that we can use? Always that odd idea. In a limit law that we talked about before, doesn't have any things to do with trigonometric function yet. Then second, right, since I cannot use the limit law, so second, I will think about, okay, can I simplify? Because our limit of the original function is the same thing as what the simplified of functions, limit of the same simplified function. I cannot simplify either, because sine functions, how are you going to simplify? Because this is one whole operations, right? Operator. So in that kind of situation, that's where you're going to start thinking about the theorems, because applying the theorems, like thinking about applying theorems in the first place is like a little bit more complicated. So you want to think about the order that I just mentioned. Can I apply the limit laws directly? If not, can I simplify and then try to apply the limit law? Right? Those are the tricks that we learn. Only if those two doesn't work, now we're going to try to think about what can any theorems apply to find out the limit of this function. So in this case, the first two doesn't work, so we're going to have to think about the theorems. So the only theorem that we learned so far is a squeeze theorem, right? So in order to use the squeeze theorem, first I need to make sure what I have this case one, the criterion one has to be met. The criteria one is what? Try to find out the lower bound functions and the upper bound functions of this middle function. So I have to think about, let me write it this way for something that we need to consider. I need to think about what is my f functions, the lower bound, and what is my h functions, that is the upper bound, of what? Of the middle functions that we want to talk about, which is we'll be naming g function, which is x squared sine of 1 over x. Okay? So we want to know what is this two function. We will be dealing with, because of this is the first time we've seen this theorem and then how to apply it, we will be dealing with a fairly straightforward situations. And I have one example that, help you to see the construction of this upper bound and lower bound functions can be very complicated, right? But we will be dealing with only like, the straightforward situations. So what I want to do is I want to, start looking at, okay, let's consider this. I cannot consider the whole functions right away. So we know that the sine functions is between 1 and -1. Right? The value of sine is between 1 and -1. And, from here, we can start continuing like, can I continue from that on? Right? So that sort of tell us like, a bounded situations already, although we haven't find out the bounded functions that we want. And then what we're going to consider is what we want to get our g functions in the middle, and what missing is the x squared part. And since x squared is a positive value for any x value, so therefore if I multiply all three parts of the inequality by x squared, then I will get the same thing. The inequality doesn't change, right? Because of multiplying by a positive value. So now I have negative x squared is the lower bound, and then positive x squared is the upper bound of the desired functions that we want. So this is basically helping us to get our first case, right? Our first case. So now I can state this, right? I can state this is our first case. Now, looking at the second case, second criteria. What is the second criteria that we want? We want to find out the limit as x approaches to 0 of negative x squared, the lower bound, and the limit as x approaches to 0 of the upper bound x squared. That's the case 2 that we want, which is, in this case, we will see that direct substitution is applicable, so it will be -0 squared, which is 0. And direct substitution is applicable, 0 squared is equal to 0. What tell us in this case is what? These two limits are the same. So limit as x approaches to 0 of negative x squared is equal to limit as x approaches to 0 of x squared. And which is what? That is the case 2 that we want to, the criteria 2 that we want to see and meet. And finally, because of these twos are met, then I can use the squeeze theorem. So finally, I can say that this, let f of x be equal to negative x squared, g of x be equal to x squared sine of 1 over x, and h of x be equal to x to the second power. All right. With, because we already know that f of x is less than or equal to g of x less than or equal to h of x. Okay. And limit as x approaches to 0 of f of x is equal to limit as x approaches to 0 of h of x, which is equal to 0. Therefore, this is important. You need to give credit to the theorem that you are using by squeeze theorem, limit as x approaches to 0 of what? X squared sine of 1 over x, which is g of x, that is equal to 0. Therefore, we show what the question just wants. And that is the applications of or using the squeeze theorem on very straightforward case. And the next example will be very similar to this one. So let's try to take a look at on that. So the next example asks us to prove limit as x approaches to 0 from the right side, square root of x times with 1 plus sine squared 2 pi over x, that is equal to 0. And in this case, you can see that now x is not approaching to 0, it's approaching to 0 from the right-hand side. And that makes sense because of what? The square root portion. Remember the square root graph, square root of x, only what? Domain is only from the right side, right? Of 0. So, but the key thing is like, trying to show, right? This is equal because we are trying to prove. So, proving, proving identity, this could consider as identity idea, right? Because of the equations. We can start from the left-hand side and then prove to the right-hand side to the left-hand side. So the key thing is like, from the complicated part to the simpler part, that's easiest to approach. But from here, what we're looking at it, the limit laws cannot apply. And I cannot simplify this given functions of the limit. So I have to think about like, using the squeeze theorem. So my, g function, like in the previous example, we'll be considering what this entire part right here. Okay. So I have to think about, hey, what is my f functions? And my g functions is this entire part. And then what is my h function so that I can make it bounded between those two. And the good thing is we know that there is a sine functions involved. So I can start attacking like the previous example. Hey, this sine of 2 pi over x, that must be between, right, 1 and -1, right? The output value of sine function. Because I don't have any amplitude, so therefore this is only between 1. Then we are not interested in looking for sine of pi over 2. We are interested in sine square. So if you're raising the power 2, then what happens is what? All the negative value become positive value. So that means all the negative sides is gone because it's going to be positive. So where we are starting is, remember, sine is oscillation functions. So we will be starting from what? 0, because we're only going to be talking about a positive value when you square it. So that is a slight difference from the previous example. And then we're going to slowly work on to the functions that we want, right? So that I can find out what is the bounded functions, upper bound and lower bound functions that we can use. So saying that the next one will be, I'll be adding 1 to every single part. And then lastly, I'm going to multiply by square root of 2 or square root of x to get to the point that we want. Right? So now this allows us to see what is our lower bound functions and upper bound functions, which is this one, square root of x, and then square root of 2 times square root of x, our lower bound function and upper bound function. Right? So this is the criteria 1 that we want to look for. So now the criteria 2 that we want to look for is looking at the limits. Are the limits going to be the same or not? So the next part that we want to look at is this. Limit as x approaches to 0 from the right-hand side of square root of x. What is that value? And the limit as x approaches to 0 from the right-hand side of what? 2 square root of x. And this is basically what? Square root of 0 is equal to 0 using the limit law. And for this one, it will be what? 2 times square root of 0. That will be also 0. So we can see that, the second criteria that we want also met, which is limit as x approaches to 0 from the right-hand side of square root of x is equal to limit as x approaches to 0 from the right-hand side of 2 square root of x. That is equal to 0. And this is the criteria 2 that we want to meet. So therefore, now I can basically put my conclusions for this example. Right? Now I can say that let f of x be equal to square root of x, g of x be equal to square root of x times 1 plus sine square 2 pi over x, and g of x, h of x equal to 2 square root of x, with knowing, right, because we found the bounded function, with knowing that f of x is less than or equal to g of x and less than or equal to h of x, and limit as x approaches 0 from the right-hand side, right, of h of x, I would say that f of x is equal to limit as x approaches to 0 from the right-hand side of g of x, h of x is equal to 0. Therefore, by squeeze theorem, limit as x approaches to 0 from the right-hand side of square root of x 1 plus sine of 2 pi over x, that is equal to what? 0. And that concludes for this problem. You might feel okay when I'm going over it because I'm guiding you through, but when you sit down, you really need to start thinking carefully, right, how to create this bounded function. A lot of problem that we're going to be dealing with will be pretty straightforward one, right? Not the complicated one. So let's take a look at on the next example. The next example, say that suppose that limit as x approaches to a of f of x equal to 0, and absolute value of g of x is less than or equal to m. For a fixed m, that means m is a constant. And for all x is not equal to a, prove that limit as x approaches to a of f of x times g of x is equal to 0. So for this type of problem, you can see that there is no numerical value of functions and the formula of the functions at all. So how do we deal with this, right? So first thing, what we want to do is we want to prove that the limit of the product is equal to 0. And what is the things that we know? Right here, this is something that we know, the given. The limit of f of x is 0 as x approaches to a is 0. And also, absolute value of the g function is less than or equal to a constant. So what we want to do is we want to use, this squeeze theorem idea to apply this. For the squeeze theorem, the first criteria that we need to have is what? The bounded function. So we're going to try to create bounded functions. So in this case, we'll say that, starting point will be here, one of the given absolute value of g of x is less than or equal to m. By the definitions of the absolute value inequality, I can use the equivalent definition saying this g function is bounded between negative m, the constant, and positive m. Now, the functions that we want to find the limit for is f times g. So therefore, what I'm going to do is I'm going to multiply each part of the inequality by absolute value of f of x for any x value, right? For any x value. And the reason why I'm using absolute value of x is to make sure that it's a positive result, right? So that the inequality will not change. And then that will save us a lot of cases to deal with it. Then what we want to do is we want to find out, the limit of each case, because what we want to do is we want to find out the limit of f times g of x. So in this case, I can basically take the limits on each part, right? So I can say that, hey, the limit as x approaches to 0 of what about absolute value of f of x times negative m. And this is basically negative m. Remember, m is a constant times with, the limit as x approaches to 0 of the absolute value. Not 0, my bad, a. Okay, we are talking about in general, a of f of x, which is going to be what? Negative m times the absolute value of 0, because here's the other given. Limit as x approaches to a of f of x is equal to 0. So therefore, that gives me 0. So here's a criteria 1 that we have right here. Here's the criteria 2 that we are looking for. Okay. Then I can do the same thing, limit as x approaches to a of what? Absolute value of f of x times m. That will be the same thing as m times absolute value limit as x approaches to a of f of x. That will give you m times absolute value of 0, which will be also 0. So that gave us a criteria number 2 that satisfy, which is the lower bound and upper bounds have the same limit, right? So limit as x approaches to 0 of, absolute value of f of x times negative m is equal to limit as x approaches to 0 of absolute value of f of x times m, which is 0. Now I can say that therefore, right? Therefore, by squeeze theorem, right? For any x value, right? For any x value, the limit as x approaches to a. I keep on saying 0 right here. My bad. Sorry. Here's a. Here's a of absolute value of f of x times g of x, which is the middle functions, that must be equal to 0. Right? Since this is for any x value, that's always going to be true, right? So, the f functions will be always true, because when we talk about either positive side, absolute value, we'll be talking about positive side or negative sides, but the negative will be a factor that I can factor it out. So this will be same thing as saying, equivalently saying, the limit as x approaches to a of f of x times g of x is equal to 0. And that's conclude this example. Notice that the next example right here, limit as x approaches to 0 of sine x over x equal to 1. We look at this problem geometrically on the section 1.5, the previous section. Right? And this is the example that I'm talking about. The constructions of lower bound and upper bound will be, very complicated in some situation, right? So, but to save the times for this like recording purpose, I'm not gonna go over on this example. This example is in the textbook, and I will be more than happy to go over that, the construction from the scratch, during the office hour. But this is the limit that you really need to remember so that we can use, right, on a lot of different cases later on, and also in the next example. So the next example, I want to use this to apply it, but this is taking like about at least 1 page long, so I'm not going to go over this. Okay, but feel free to like come in and ask me during the office hour. In a regular semester, I take time and go over it because of the recording. I don't want to be like a very long recorded video. This is already like an hour long, at least I think so far. So let's quickly finish that by this next example. We want to show that limit as theta approaches 0 of 1 minus cosine theta over theta is equal to 0. Right? So to show this is true, I'm going to start from the left-hand side. So limit as theta approaches to 0 of 1 minus cosine theta over theta. And what I would do is I want to use the, the limits of sine x over x that limits. So I'm going to try to rewrite everything into sine. So therefore, what I'm going to do is I'm going to multiply this by the conjugate factor. That's to help us to use the identity. That's why I mentioned that you need to remember the identity. So 1 plus cosine theta, 1 plus cosine theta, and which give us limit as theta approaches to 0 of 1 minus cosine squared theta times with theta, right, over theta times 1 plus cosine theta. So this gave us now limit as theta approaches to 0 of sine squared theta over theta times 1 plus cosine theta. And what we're going to look at right here is simply breaking it down into the situations. Limit as x approaches to theta approaches to 0 of sine theta over theta times with another case sine theta over 1 plus cosine theta. I just break it down into two fractions multiply because this is something that we already know, right? So now by using the property, limit law, I can say that limit as theta approaches to 0 of sine theta over theta times with limit as theta approaches to 0 of sine theta over 1 plus cosine theta. And this entire, right, expressions, the limit value is equal to 1 that we already know. For this second portions, I can do the limit law because sine and cosines are like polynomial functions, right, everywhere. And if you substitute the value, then you will be able to get, sine of 0 over 1 plus cosine of 0, and which was going to be 1 times 0 over 1 plus 1, that is 1 times 0 is equal to 0, which is the right-hand side that we want. And these two, right, limits, you might want to remember that to use it in a lot of other problems, okay? And this is the end of sections 1.6. It's very long sections because I give a lot of examples, right? And the homework is all the way in the beginning of the lecture. So make sure you practice enough, okay? And practice carefully on using, practice using, these limit laws carefully.